Good morning, mathematicians. Do I have to turn over even more so I'm not shrouded in darkness? Why is this... Wait, why is this half of my face shrouded in darkness? I don't know. Oh, now I'm way too light. Well, that's how it goes. Is it better to be washed out in light? Holy moly. Or faded in darkness? Oh, now what's your philosophy of life? Well, live in the darkness or live in the light? I guess I'm in the light now. Yeah, okay. Let's talk about some random stuff. Yeah. I'll tell you about something I got stuck on a little while ago when I was trying to, I was planning to continue my Rings and Modules series. And something that happened was, well, one of the things is that I was going to prove. Statements I was going to try and prove. What is going on here? Okay, the stylus is working because I can move the pen. Is it OneNote that's frozen? Oh, it's OneNote that's frozen. Of course. Of course it is. Kill it. Kill it with fire. Die, OneNote, die. If I say that kind of thing on stream, do I get demonetized? Okay, let's try that again. Nice, there we go. So, what was I trying to prove in that series? Hello, Boris. You did make it in time. I started late today. I was thinking about the category of R modules. And in particular, this is an example. Well, it's an abelian category. What does that mean? It means several things, but in particular, it's an example of an additive category, which is part of the definition of being an abelian category. What does that mean? That means that all of your Hom sets have the structure of an abelian group in a way that's compatible with composition. So of course, if you have two module morphisms, you can define the sum of those morphisms to just be the function that returns the sum of the individual arguments in the target module, and that will give you a module homomorphism again, and it distributes over composition, right? So that's what makes it an additive category. And actually, well, that's what makes it a pre-additive category. And then to be an additive category, it means that you have all both coproducts, finite products, and coproducts. So in particular, what's really interesting though is that having finite products and coproducts actually allows you to define a pre-additive category. So really the essential feature here is just having finite products and coproducts. And in fact, the sort of interesting theorem is that there is, on any additive category, there's a unique way to make it an additive category. And since there's a way that comes just from the structure of products and coproducts, this means that every additive category can be realized as such, essentially in an internal way. So what do I mean by that? I mean, pre-additive are your favorite of that because of Karoubian envelopes. Oh, I don't know about Karoubian envelopes. Karoubian envelopes. Idempotent completion. I think I have maybe come across this at some point. The classification of the idempotents in C by means of the auxiliary category. Oh, interesting. Taking what does pseudo-abelian mean? It's a category that is pre-additive, and okay, every idempotent has a kernel. Interesting. Hello, MD. Sheafification. Yes. Are you asking about sheafification, or just generally enunciating your love of the concept? So I sometimes go around just saying sheafification to people. You get an awesome proof of Sarah Swan? Really? Oh, interesting. Huh. Really? Where can I find the proof of Sarah's? Oh, it's here. The category of vector bundles over a paracompact space is the Karoubi envelope of its full subcategory of trivial bundles. Really? Trivial bundles, so just the n-dimensional trivial bundle? And you take the Karoubi envelope of that and you get the category of vector bundles? Why isn't there a citation for this? Where do I read more? Karoubi's book. Oh, okay. And this is in fact a special case of the Serre-Swan theorem. Oh yeah. And conversely, the theorem can be proved by proving both of these facts. Right, global sections is equivalence between trivial vector bundles and free modules, and then using the universal property of the. Wow, I gotta find. Good MD explains, as you should. I think I've mentioned this before, but you know how there's sometimes like religious people like standing around downtown places with just like Bibles, just like waiting to talk to people. One of these days I want to do that with math. I just want to have stand out there with my favorite textbooks and some like fun toys and examples. And then, yeah, just stand there and talk about math. I really just need to do it one day, but you know, I feel so like busy. It's like I got other stuff to do. There's math to be done, you know. One of these days. I'd film it. Oh, I could film it too. That'd make great YouTube content. Yeah. So, okay, wait. Karoubi's book. Which book is that though? Karoubi book. K-Theory by Karoubi? Wait a second. I have a hard copy of this book. Is it in here? Hello, Arad. That's actually K-Theory, yeah. I've got a hard copy of this book recently, from some. Wow. Okay, great. Well, this will be my new bedtime reading. Is understanding the proof. Wow, that's exciting. That is exciting. Where's Sarah Swan? Okay, chapter 6. Algebraic properties. In the section, we proved category vector bundles, pseudo-additive, every projection operator. We deduce Sarah Swan. Awesome. This is amazing. I can't wait to go to bed tonight and read this book. The math grind is grinding, Dason. Fun fact, Karoubi envelopes are also used in the construction of the category of pure motives. Huh? Hello, Emile. Hello, Belgium. Please say hello to all of Belgium for me if you can. Doesn't sound easy, but if you can. Wow. Maybe I can understand the category of pure motives eventually. Maybe it's within reach. Oh yeah, NLab. This will be the most understandable answer. Growth in growth. I like how this is all one word. I mean, there's enough. I feel like there's enough explanations of things that start off by growth indeed conjectured that we could, there's justification for turning this into a single word in the English language. Yeah, exactly as you say, Arad. He conjectured that every Weil cohomology theory factors uniquely through some category, which he called the category of motives. Smooth projective varieties. For smooth projective varieties, such a category was given by Grothendieck, called the category of Chow motives. Okay, this makes sense. That's not unreasonable. 57, indeed, the only composite prime. MD knows what's up. Category of correspondences. Oh, is this what people mean when they mean correspondences? Oh, there's a Karoubi envelope. The Karoubi envelope of the category of correspondences is called the category of effective pure motives. Okay, interesting. You gave up on what a Chow group is? You shouldn't. You should go read the book 3264 and all that. Mind you, somehow I found that book very... I didn't find it made the most sense in the world. And, I remember my first time reading it. No one ever... I don't think they ever say in the book what it means to be generically something. And I was like, why aren't you guys defining this term? I guess, the assumption is that you would have read enough algebraic geometry before approaching that book to know what it means for a property to be true generically in a formal sense. But I don't know. I hadn't come across that term before, and it really bothered me. But Chow groups aren't so bad. At least if you go try and understand the Chow group of a Grassmannian or something, that's a good place to start. Okay, I mean this makes a tiny bit of sense to me now. Karoubi envelope of the category of correspondences. And the category of correspondences is yeah, I guess I'm a little confused. What are objects? Objects are smooth projective varieties. I see. Okay, and then the Hom sets are given by these sums, and these are the Chow groups. Okay. It's not a well-received book among mathematicians. Is that true? Hello, Jack. I mean, I'm a mathematician, technically, and I received it well. I mean, yeah, in terms of rigor. Hello, Kiki. Is that how I say your name? Kai, perhaps. I'm good. How are you? Ni hao. Chow motive. Effective motive or Chow motive. Yeah. Okay. Well, that's all cool. Well, let me finish telling you guys where I got hung up on in this other place. we really took a bit of a detour there, which is good. That's what we're all about here, taking detours. Yeah, I mean, okay, but let me say, yeah, for whatever non-rigorous faults, I mean, I did find 3264 a difficult read, but I think there are some nice explanations of stuff. I think it's maybe not a bad place to learn some things and see some stuff about Chow groups in action. But yeah, they do appeal a little too much to geometric intuition for me. Which is to say, I mean, that seems like a weird thing to say. I don't think you could ever. By which I mean they're just like, oh yeah, like obviously these spaces intersect or something, and it's like, well, could be a little more formal in your explanation, but it's not other place, it's one place. You mean to learn about Chow groups? No, I'm sure. No, for sure. There's other places. You could. Hartshorn talks about Chow groups. So certainly there's other places. Now maybe you say Hartshorn's not any better for you, but I guarantee you, if you just spend some time searching, you can find some other nice explanations on Chow groups. Homology over topological spaces that are behaving like groups. Well, often homology, we take it to have coefficients in a abelian group. So that is a common thing. Chow groups are definitely not identical to Lie groups, though. Not even close, unfortunately. Yeah, I mean, Chow groups are, yeah. These are often like finitely generated abelian groups. Yeah. But in your opinion, looking at it geometrically, discovering of seeing new geometric structures can be translated back to algebra. Yeah. Well, we're physics positive on this channel, MD. We are physics positive on this channel. Lie groups are cool, and I've definitely yapped about them a bunch here before. Yeah. But getting back for a moment to this other thing. So if you have a category that has finite products and coproducts, then you can define, well, if we take any object and we take its coproduct, then, and we take the identity maps here. Oh, let me give myself a bit more space. And we take the identity maps here. Then we get a unique morphism making this diagram commute, which we call this would be the codiagonal map. And then simply reversing all the arrows for the coproduct. Well, in this case, because we have, I should say we have all byproducts. So it should be that products are isomorphic to coproducts. So it's an object that simultaneously satisfies the universal properties of product and coproduct. That's crucial, which is satisfied in the category of modules. We then also get simply reversing all the arrows, and because this thing satisfies also the universal property of the product, reversing everything but still using the identity, we also get what's called the diagonal map. For what I hope is obvious reasons, if you work out what it has to be, it literally, take as your concrete model, like, what you normally think of this as, some module on the Cartesian product, and it, literally, sends A to AA, right? So now, our goal is we want to define in a purely categorical way. We want to define what it means to add two maps, alpha and beta. And let's see. Can I do this from memory? How does this go? How does alpha plus beta go? Well, we get, right. So we get a map. We get a map from, we also get a map here that's alpha sum beta by universal property nonsense. And then we define the addition of alpha and beta to be, first apply the diagonal map of A, then apply alpha sum beta, and then apply the codiagonal map into B. And so it turns out that this defines an abelian group structure on all of your Hom sets in a way that's compatible with composition. So in other words, this makes our category into a pre-additive category. And what was I going to say next? Yeah, and then the big takeaway is that you basically use this to prove that this agrees with any other pre-additive structure you can put on your category. So in particular, like if you work out what this is, you'll find it literally is the sort of this more naive set theory based type definition for the additive structure on modules. So somewhere I got tripped up though here. Like in a separated morphism, kind of, yeah. Oh, you're right. It should be. Sorry, you're totally right, Jack. I wrote nonsense. Somebody wrote nonsense. And it was me. Big surprise. Yeah, well, I mean, yeah, you could maybe try to explain this to a high school student via multiplication. Wait a second, is that true? Because I mean, in the ordering category of integers, we do have. I don't think we have byproducts though. We don't. We have products and coproducts, but they're not byproducts. So, yeah. But then the one thing I tried when I was trying to make that video, and then I ended up spending too much time on it, and so I abandoned the entire series and decided to just work on my thesis instead. So here's a challenge to all of you: is I got a little tripped up on proving the, how do I adjust the thickness? It's a little thick. Was proving the associativity. I found it was a little tricky. To prove the associativity of this addition operation. I know there should be some slick way. I think I proved inverses and the commutativity and all of these other things, but I found it a little tricky to do this part, right? So what does the statement say? It's like co-diagonal to B A sum alpha sum beta diagonal A. Well, I drew a lot of diagrams. I drew a lot of diagrams and tried to prove it, and it was not. Oh, and then we have plus, right? And then we have plus here, so this should be. So let me write out the whole thing, and then I'll start doing the diagrams. But then I tried. It took a lot of space. I had to write a whole bunch of diagrams on a bunch of whiteboards, and it yeah. Okay, let me do it this way. So I'll start with the left, and let me go co-diagonal B alpha plus beta summed with gamma composed with delta, or diagonal. Look at me writing nonsense all day long. Right. So it should be this equal to this, and then we could unpack this even further and get that co-diagonal B, put braces here, co-diagonal B composed with, wait a second, yeah, composed with codiagonal B composed with alpha sum beta composed with diagonal A sum gamma composed with diagonal A should be equal to, see, I mean, as you can see, writing out the diagram for this is quickly going to become a nightmare. Alpha sum codiagonal B composed with beta sum gamma composed with diagonal A would the addition operation be the unique morphism as the composition of unique morphisms? Would the addition operation be the unique morphism? Yes. So, I mean, I think the strategy would be to prove basically that like this basically has to satisfy a certain uniqueness property, like this fits into a certain commuting diagram, and so the strategy would just be to prove that this fits into the same commuting diagram. And I think that's what I attempted before, and then I just got lost in the sauce of it all. Yeah, so I mean, maybe, yeah, this is alpha, so this is alpha, beta, gamma. Well, I am about to start drawing the diagram, so don't you worry. So we begin, so we have A, diagonal into A. Diagonal. And then we have what? Alpha plus beta sum gamma into B direct sum B, and then we have the codiagonal B into here. And so, yeah, the strategy would be, so this other one is alpha plus beta plus gamma. I mean, if we could show that this commutes with everything. So, I mean, that map also starts off going through here, but then we take this alternative route. Oh, each of the pens have their own thickness of alpha plus beta plus gamma, right? But we don't really have like we sort of are missing commutativity at this point. So I guess this is the thing, but I mean, we're not going to have commutativity at this point because these maps are different. So, yeah, I guess what we need here is really, I should be drawing it this way. So, and this is indeed the diagram I drew before, where I previously got stuck, but maybe we'll try and get unstuck on stream together. But we'll have to finish it tomorrow or over the next couple days because I want to go soon and work on my thesis. This characterization of pre-additive is really nice. Agreed. Yes, exactly. It's internal to the category. It's also what's nice about stable infinity categories over triangulated categories. Right, I was reading about that the other day, right? Because somehow the shift comes internally, right? There's some way to define the shift internally. If the delta operation, I think you mean del, was a natural transformation, I guess, is it a natural transformation of functors? I guess it is, right? I mean, if you send an object, you take the functor that sends an object to the sum of itself versus the identity functor. Like, I guess del can be viewed as a natural transformation from the identity into the functor that sums an object with itself. It should all get into b plus b plus b eventually. Then it comes down to the associativity of the direct sum. Yeah. Yeah. Ja, das ist richtig. Das ist richtig, ja. Yeah, I wonder. I mean, it just gets messy, but like, yeah, I guess maybe if I then try to unpack this arrow, and that's what I tried to do before then, is I tried unpacking each of these arrows and then proving, you know, I wrote some arrows between things, like, you know, ones that swap factors in the associativity of the direct sum, and then I tried to, you know, prove each little part commuted, and eventually get there. But yeah, I just got hung up. But so maybe we'll try this tomorrow. Yeah, but I think the commutativity was easier. Like, I was able to get the commutativity pretty much right away. I think I proved that one back in the day. Back in the day, a couple months ago. But maybe tomorrow I'll go through the seeming nightmare of unpacking the whole giant thing. And then you'll all be credited in my video whenever I get back to that series. So, okay, go prove this. Go prove this for me, and then help me finish it tomorrow. How about that? That's everyone's homework. Okay, go prove it.